Our next presenter is Hans Post, EMC Manager with Magnetic.
Thank you very much that you're here and not in the sunny outside, relaxing somewhere where I would like to go to. So I would like to talk about some things, maybe hopefully it's interesting for you, and it's something what maybe you didn't hear before. It's about motors, it's about protecting motors, getting them more reliable, not only the motors, although the variable frequency drives and other stuff. And what we're doing is, I would say, a little bit unusual. Everybody is doing something with brushes to get some protection of the motor bearings or something like that. We are not doing that. We are adding some of this cores, which you can see up here, on the cables and say this will help you. And I promise you, it will. The problem is to understand it. At the end, it's very simple. At the beginning, it's a little bit unusual. What we're having up here, that's nothing else than a common mode choke with one turn. So what we're doing is, we are putting this one on a special place and tell you about how this is working. But before I start that technical stuff, I would ask you, I would show you something where we do not need common mode chokes, but especially not nanocrystalline material or something like that. I have seen this grinding machine in Sri Lanka. I loved it. It makes a fantastic curry. And it's running since the 50s without a bearing damage coming from electro-erosion, believe me. So this is one of the things where we do not need it. But if you have something like this stuff here, like wind turbines, like chillers, something like paper manufacturing processes, solar panels, some other stuff, although pumps, fans, something like that, where you're working with variable frequency drives, I guarantee you, you have something like common mode currents, and this common mode currents find a path which is mostly not this way what you expect at the beginning. One of the most dangerous paths is what happens on the common mode current is going over the ground, going to the ground over the motor bearings or over some insulation. Yeah. That means, to show you a little bit or the overview, what I want to present you is what are cool blue inductive absorbers. Cool blue, why you think it's called cool blue? Because of the colors. Thank you. Yeah, and if you put something like a ferrite or something like that over a motor cable, it's getting very hot. Because in saturation, I think it's something like that. This material stays very cold, cool. Where they are used, you will see that later on, what is advantage compared to other solutions, which improvements we have done in the last years, because this is not totally new. We have really some nearly 8-9 years experience on that material, and we improved it. Then there is an outview on different shapes. That's not the only shape that we have, but this is just to show you a little bit. And other products where we use this nanocrystalline material. For the starting, what are cool blue inductive absorbers? What you see here is a nanocrystalline tape wound core. The thickness of it is about 20 micrometers, which is really thinner than a hair. And you have seen Arnold maybe before. This is much, much thicker than this one. So the frequency behavior of this one is much better. So we are talking about frequency response up to the 100 megahertz, where this material is still working. So, and it's needed to work really in the megahertz range, and I will come to this point later on. It gives you just another thing, not only the thickness of 20 micrometers is very interesting. What we're doing is, this is a thin tape, and we have crystals inside, and these crystals are insulated. And the thickness of the crystals is about, I would say, 20 nanometers. So if you just have 20 micrometers thickness, then you have the structure of the tape already inside, cut it down to 1,000 slides, and this although in small areas. Why are we doing that? Because we can, I know, but no, because we want to reduce the eddy current. And eddy current is directly related to the area or to the volume. So if we reduce the thickness, like Arnold is doing, then it's reduced. But we do it 1,000 times more. And then the losses are really a 1,000th part of standard silicon iron, just to give you an idea. If you do this, then at the end, you get something like thin foils. These are coarse, not annealed, but it's called amorphous tape. And later on, the know-how is making out of this amorphous tape a nanocrystalline core. Okay, maybe just to give you an idea how this thin material is produced. What do you see up here? That's a melt about 1,200 C, lapping on a fast rotating cover wheel, shooting down with a speed of 100 kilometers an hour, whatever it is in miles. And yeah, and then you have already shooting out the end width of the tape. That means the width is the height of the core. Yeah, so that's one. And then you can roll it to that one, to the ring, what I have seen, what I showed you before. In this, this process has a cooling speed of 1 million degrees per second. You believe that? I hope. If not, try it. It's looking easy, but it isn't. The reason for that is if you melt the iron, because basically the alloy is the iron, and you cool it down slowly, it gets crystals. But what we don't want to have crystals in a big, huge size. We want to have we want to have an, I would say, something like amorphous alloy. And this we only can reach if we can freeze it. That means immediately after the liquid phase, it's frozen down, so it's amorphous. It's all called metallic glass. Yeah. That means if you now roll this tape to a core, it has nearly no magnetic performance. So you cannot use that core. So then you need a second step, that's called the annealing. But I will come to this point later on. Here you just see it's inductive heating, that's just a lap. So this shoots out, and then we catch it up and just wind it to a core. Okay, where are these thin metal glasses, sharp like razor blades, used? For example, here you have an inverter, variable frequency drive, you have a motor, and you just put these things over the cable. And then you measure the common mode. The common mode is that one when you put the clamp over all three lines of the motor, and then you measure the peak current of that stuff. And here you can see you have very high frequency noise on that. And when you put it over, it's really reduced to this undangerous peaks. I will come to that point later on, how to define what is safe and what is unsafe. Here you can see a little bit, they are riffles. That's a typical thing what you see on the motors pitting or something like that. They are really deep investigations where it's coming from, but I can say the root cause of this pitting or these riffles, what you see here, is electro erosion. That's all. Yeah, some applications. I said it already before. I'm working now for over 8 years in the wind turbine area. There we are single source and one of the biggest producers. That's the only way how to get rid of the common mode noise there. If you're interested, we have a booth downstairs. I can explain you a little bit. We are a single source on one of the biggest chiller producers. They are using the same, and they really save money on that. Why? Because if they put in the cores, the common mode noise is absorbed in here, and they don't need costly hybrid bearings. But I can go to this point more in detail later on. Here, this is 5 kilo. This is a 5 kilovolt or 4 point something kilovolt application. This was a grinding down a hill to dust. Why the hell we should grind down a hill, especially it's marble hill to dust? Do you have any idea? I didn't know it before. If you have a very good paper, it's very heavy. And to whiten the paper, you have 30% contained of marble dust inside of the paper. I hope you learned a little bit about that. I learned it. Okay, other applications is solar cells. That means the solar is creating a DC. This DC is chopped, getting back to the grid, and you get big, big, big common mode currents. And this is not allowed to feed back to the grid. There you see one application. There are 5 cores stacked, but this is in the megawatt range. So these are only the 5 cores which are stacked in the cabinet. You need 45 cores more, just to give you an idea. But this is the only solution. The other solution is to make a transformer. And you can imagine how big this transformer in the megawatt range would be and how many losses you get. So this is really a good running solution for now, I would say over 5 years. Okay, what is the advantage? Easy to mount and to retrofit. Yes, it's very important. If you have an already existing application, maybe running without a variable frequency drive, and you want to mount a frequency drive, then normally you have to use shielded cables, because if not, all your sensors around are getting crazy, or something else. And so that means you can just put this cool group force over it, and you get rid of the common mode current and all the radiated emissions. Easy to select. I will show you later on. We prepared some tables. Tables means we have some application leaflets. It's very thin, so we can read it too. So just open it, and there are two tables, and on these tables you can see the horsepowers and the cable lengths, and you see which course you have to put over in which amount. So that's very simple. Yeah, what is the next advantage? I hope I can see that. Effect is immediately seen, the peak current. Yeah. If you measure the current, you see often you look on the average or on the RMS value. In this case, it's not correct. We need the peak value on that. I will come to this point if somebody is interested to explain it. But if you put the course directly over it, you can reduce the amplitude of this common mode currents significantly. We had a motor with about 50 kilowatts, I have to say. I'm coming from Europe, so Germany. And we just put the course over and reduced it from maybe say 80 amps down to 7 amps, just to give you an idea. And that's really that point where we had to get to be sure on the safe side that this is not more dangerous for the bearings. Working against parallel conducted and radiated emission, I already said it, maintenance free. Sorry about that, I'm not the sales guy, I'm the head of the development. Our sales guys are getting crazy. Normally they want to replace it every 5 years. I have to say we have no aging process on that. So sorry, if you put it in, you can keep it as long as you want. You pay for that. Yeah, next point, working over decades, I said it already. Yeah. And there's one point, there's another solutions that often a hotel, I said it before, you can use insulated bearings, hybrid bearings or something like that. It's working too. It's a nice story. They have really some advantages, but they have one really disadvantage. These are the costs. You put in a hybrid bearing, maybe for a 100 horsepower motor, we're talking about, let me say, no, sorry, it's not 100 horsepower. It was about 500 horsepower. Then we're talking about some specialists here, a few $1,000, maybe $1,000 to $2,000. And if you put in some course of that, we are in the region of a few hundred. So you can imagine, it makes really sense to think ahead and just invest in that one instead of putting in a hybrid bearing. And there's the next point on maintenance reasons. Although a hybrid bearing has to replace typically wise in the chiller area every 7 years. So then you have to invest the 2,000 or more bucks again. This course you don't have to replace. Okay, which are the improvements? This is already detailed. Just want to tell you, we started already with very good performance. This is a tape wound core, silicon iron based, but very thin, very, I would say, structured. So we had already very high inductivity. Just to give you an idea, the standard permeabilities, what we can do up here is about 80,000 Farad, typically 5 to 10,000. But this is already very good. What we did is we improved the tape and the annealing, and this gives you a much better performance. And at the end, you see you have an advantage of over 20%. The different is that, maybe it's very interesting on that one, you see on that scale here, it's related to the Cool Blue and the Cool Blue Plus. So if you have a space problem, you can reduce maybe 5 cores to 4 cores, just using instead of Cool Blue Plus. But this is just for insiders. Okay. Maybe to show some possible mechanical dimensions. We do not have only round cores, we do not have only oval-shaped cores. We have some cores which are more in the direction rectangular shape. It's a funny thing. We name it oval. I think, what is racetrack shaped or whatever? How you name that? Different names on that one. What is good for you? What do you say? Something like that. So how we say oval, but we know this is not oval. Just to give you an idea in which dimension range we are talking. This is only an overview in the typical bigger horsepower ranges. So I would say here you see 1/2 meter size. So it's really a huge core what we can do. And here we are in the 60, 70 millimeters, but we can go down to 10 millimeters. So 1/2 inch is theoretically no problem. Maybe less. It's depending what kind of application you have. Just to show a little bit that we do not have only round, oval-shaped cores or rectangular cores. There are some developments where we put this nanocrystalline tape, we named it our trademark, it's Nanopart, although on strips or on blocks. The background for that is this is used for wireless energy transfer. If somebody's interested in that, I can talk about this maybe half a day. So it's just an idea. So So there are different shapes of that material, what we can offer, but for the increasing of the performance of the motors, I think this is not directly that what you need, but it's interesting for other applications. Yeah, just short middle resumption, I have to say. Cool loop cores are increasing the reliability of the motor and complete machines in case of maintenance and availability. How can this course do that? Very simple. If you put the cores in, the common mode current cannot destroy, so the motors are running out longer than your maintenance cycle. And if you're able to do this, then you are in a good cost margin. Yeah? So that's the target. So in earlier times, you just put the motor on the grid, and you say it's working for a decade if everything is perfect. Now you put a VA, the variable frequency drive on it, and the motor can stop, and this is a real life after half a year, and the bearing was damaged. Yeah, so and that is absolutely not acceptable for each application. That's not only the cost on the bearing, not only the cost on the motor. One important thing is the downtime. That means in that time, while you have to replace the bearing of the motor, you have the downtime costs, and the machines cannot produce. So that's really a big amount, especially on the lower horsepower range. Yeah. One of the things is the cool loop cores are absorbing the dangerous electrical noise. Sounds nice. Dangerous electrical noise and change it to safe. There was a writing problem on my side. I said here it was a V, but it's F. It's okay. To save thermal energy. Okay, that's really the way how it is working. This inductive absorber, if it would be a ferrite, I would say. Then it's coming from a ceramic, and this is then you have a very good inductivity. But this is not good for the application. If you put in too good inductivity, then you get reflection on the core. You get waves, and the waves can get bigger problems than before. So that means you need on one side a very good inductor, on the other side you need, I would say, a low or good enough losses that these are not getting harmonics later on the reflections. So that means it really to thermal energy, and this is really a good I would say position or a good point to judge it. The cores have to get good warm, means and warm or something like that. Then you see they are worth for the money. If they are cold, I would say we get good sales. Yeah. Okay. Another application, you have this Nanopart cores or cool loop cores are good for EMI filters, EMC filters. They are good for transformers, and actually in the automotive area, they are really important to reduce noise for radio. So it's really all of higher frequencies than I would say the 100 megahertz. So all the head it's working. And we know everybody who is dealing with the automotive area knows that size and weight is really critical. Yeah, I said already, Google Plus has a 20% higher performance. I think the costs are a little bit higher, but that's normal. Okay, just to show you some other stuff. Where can you use these things too? I never heard about that before, but this is something like in the 800 kilovolt area. You have seen something like that? I'm not. That's called gas insulated switch. This is where you have your energy distributions. They are using something like that, and here you can see that the cores are just directly used here. And the reason why they are there is that if you switch a big voltage, you're getting harmonics too, and then you have 800 volt switch, and this gives you at the end really some big trouble, and at the end you will destroy the switch in a very short time. It should last minimum 3 to 4 decades. Yeah, if you don't put the cores in, it will be destroyed, the insulation of the whole cabinet, only by the harmonics of the switching. Yeah, now we are coming to a mixture between common mode and differential mode. I know it's a little bit complicated, but it's real life. These are the common mode cores. They are over all 3 cables of the application. I think this was a 50 kilowatt application. And one of the new things, what we found out is we can combine the common mode cores with very high permeable nanopart line absorber cores. They are on each line one. What they are doing is, if the IGBT switching, normally you have a ringing on it. And what this is doing is it is smoothing. And what I learned after half a bottle of red wine, the source of common mode is differential mode. It's like that. Because the common mode is nothing else than the difference between the three phases. So if you already reduce the harmonics on the differential mode, then the common mode is dropping down too. So you need both. But you cannot do it alone. So that means, I think you cannot do it alone with differential mode cores, that means nalas. You need the right combination between the common mode cores and the differential mode cores. May you see one strange thing what I did up here? I don't know if you have an idea for what this is good for, but it's very helpful in the real application. I hate to mount cables and dismount cables, put one core in, check if it's working or not, maybe mount two more or less. So what I'm doing is I mount more cores than I normally need. And what I'm doing here, it's just a short loop. I just have a shortcut over the core. Why? This is deactivating the core. It's really working. That means, for example, you don't know if you need two of these nalas or one. Just put in two, make a shortcut, and you see immediately the changing in the high frequency. Then you can decide you need two or one. That's the easiest way. That's the same working on the common mode cores too. Especially when you're working in the higher power range. You have the problem that the cables are a little bit thicker than my thumb. So then you can imagine to open the cables, to mount the cores, and then demount the cores again. That can last, I worked on the 6 megawatt drive, I would say 1.5 days. So with this small trick, you can easily judge how many cores you need. Good. Just to see, oh, that's an application. That was several. It was about 40 amps. And we were able to reduce the 40 amps with really, that means picture what you have seen before, with the two common mode cores and one of these nala cores. From this high frequency, that's already reduced from 40 amps. This is always, maybe, I think this should be 8 amps, something like that. And no, so it was 10 amps or something like that. And then we added the nala cores, and you see really the high frequencies is just disappearing. Why I'm really focusing only on the high frequency, not on the low frequency, which is also important, but the high frequency is much more dangerous. This you will see on the next slides. Yeah, maybe first of all I explain a little bit how to mount the cores. Yeah, just to see here a little bit. The common mode cores are mounted over the three phases, L1, L2, L3, U, V, W, and the differential mode cores are mounted on each phase. And here you remember maybe the picture was the short loop, just to show how the cores are enabled or disabled. If you are in the lower power range, there's a trick which helps to save you money. That's something like this one. To reduce the amount of cores, especially when you go maybe 10 horsepower or less, it's allowed to use more turns. That means if you have 2 turns, you do not have the double of the noise suppression, you have a factor 4. There's one dangerous thing. What happens if why don't we use 4 or 10 turns? What happens? Two things. First of all, there is a certain amount of current which you can run over the core before going into saturation. So if you exceed the saturation point, the core is not more working. So that's the maximum of the turn number. The second point is, if you put more turns on it, you have parasitic capacity. The parasitic capacity is beside of the core. That means it skips the impedance of the core. So then the core is also not more working. So there is a maximum amount of turn numbers, which is somewhere between 2 and 3, not more. Because we have to work up to 40, 100 megahertz. Just to give you an idea. Good. Yeah. Complicated. Yeah, how to select the right core. I was treated to do it, and I say afterwards it was good to do that. Just give me the kilowatts on the horsepowers. Go on that table. Say, for example, 40 horsepowers. Then you can choose the motor cable lengths, maybe 50 or meters. Then you see, okay, 40, 50, you need 4 of this cores. It's an MO49 or M367. What is the difference between the cores? The one is oval, the other one is round. Why we have these two things, round cores and oval cores? That's only because sometimes it fits better to the application. With round cores already, especially in the smaller power range. For bigger power ranges, it's not possible to put, or it's very hard to get a round core into the cabinet, maybe the size on that one. So the cabinet is for cabinets or something like that. the oval-shaped cores are better than the round-shaped cores. And here you see easy, just put two windings on it, and we have factor 4 on the performance. The same table exists for the NALA. That means for the cores which you put directly over the cable. So, but that's the same. So you go to 40 horsepowers, go down to the 50 meters, and you see one core is enough. So the second deactivated core you don't need. That's it. So that's just the size in millimeters of the core which you have to go. Good. Okay. I think the next falls are just skipping. If you have higher saturation currents, maybe up to 20, 50, 100 amps, we are able to reduce the permeability from 80, 30,000 down to maybe 8,000 or something like that. But this here is a special thing. If you already use ferrites in some applications, what we can do is and the ferrite is working good on room temperature, and you're going down to lower temperatures or higher temperatures, and then it's changing the performance. We have something like that, where you just can replace the core. It's mechanically identical to the ferrite, and they have in all parameters better performance. That means on saturation induction, on temperature behavior, everything. So that means, for example, you design a filter in your lab, working nice, then you go out in the field, you have real load on it, and then the filter is going into saturation, that means the choke. And then normally everything is too late. You can start again to design a new filter. Don't start totally new. Just go here, use the cool blue course for the new bigger than 9,000, and this course will help you to get the problems on the saturation on the ferrites. Yeah, I skipped this one, I think. I think we should get to some pictures. That's nice. How to measure common mode currents. I don't know if it's valid to everybody here, but mostly you just need only an oscilloscope. You need a clamp, which is just running. You just clamp here to the motor. And this here, what you see is just standard AC motor, and here you have a DC motor. This motor is doing nothing but load, because the motor without load has a different behavior than the motor with load. Nevertheless, the biggest common mode currents, what you get is no load, slowest switching, so highest switching frequency. Yeah, no load, highest switching frequency. That's the highest common mode current what you can get. But what happens if you put load on it? Normally the peak current is going down, but the problem is you get bigger asymmetric currents. So then it's dangerous that the core is driving into saturation. But just to see, this is just a load test application. And here you can see how we measured it. You can see a little bit here, that's just the voltages. That's a UDV and so on. That's a voltage. And what you see here, this is the common mode currents. The peaks, what you see there, this is every time when the IGBTs are switching between each phase. At the first view, it looks simple. That means you have 3 phases, you have 3 peaks, everything is nice. But this is not the real problem. The real problem is you have to get a higher resolution. And the higher resolution shows you, well, what's that here? So this is not a nice thing like this one here. This is something like which is really running over paths which you are normally not can handle so easy, because it's all the running over insulation. Switching, this is in the, I would say, 500 kilohertz up to some megahertz range. Why megahertz and not kilohertz? That's very simple. If you understand it one time, a bearing on a motor, or the most insulations of the motor, you can describe by very complex things. It's much easier at the end. Just forget that this is a bearing, just think this is a capacitor. It's nothing else. Means if a capacitor has at low frequencies, a very high impedance, we see a kilo ohms. Yeah? And when you are in the megahertz range, you are in a few ohms. So that means the bearing has on high frequencies a low impedance. So that means the current is just jumping over that and give you a welding spot on the outer rays. So what happens? If the first welding happens, the bearing is getting noisy, that means pitching and everything, and then it's too late. That means you have to avoid this. And that's a target of all what you see up here. But where are these currents coming from? The source of that one, skip that one, is really the semiconductor. So it's not the grid. We are talking about the source, that's the semiconductor. And the semiconductor is normally switching, I would say, depending on the power range in the kilohertz range, that's more, I would say, hundreds of kilowatts, or in the 10 to 20 kilowatt range, that's in the lower frequency range. This common mode current can come up here over the gearbox back in this direction, or it can come up directly over the shield, parastatic capacity up here, over the bearing, over the case of the motor, or some other passes. So that's not so easy, but that's the reason why these currents are named vagabonding currents. And the path of this you can describe, but a typical thing how to avoid it or how to reduce it was shaft. It was brushes. To use a brush, the brushes have the good thing, they are immediately reducing the voltages. The problem in this case is no dirt, the mounting is not easy and everything like that, and it's all very costly. So the target is now to avoid brushes and to use, I would say, other solution. That means like something like the cool loop cores. And again, what I said at the beginning, the cool loop cores are just doing nothing else than detecting the current and changing it to the safe energy, and then it's not more appearing, and it's all on a bypass something. So if you have a brush, it can damage a sensor or something like that in another area. Okay, just to show you what is the difference between with or without inductive absorbers, cool loop cores. If you have no inductive absorber in, you have this high frequency part. High frequency is jumping over the motor bearing and giving a spot and killing it. If you put it in, you see there's still an amplitude, but the whole high frequency is gone, and that's the target. If you're able to reach this point, you can increase the living time of the motor on really, I would say, not a few factors, it's really up to factor 10. Just to show you how we measure this was the first pictures were not without inductors, we just shortcutted the inductors. Then you get the high frequency. If you open this is just one wire through the cores. We shortcutted it, then they are not more working. You see the high frequency. If you open it, it's really smoothing it down, and the high frequency is gone, and the motor bearing is really safe on the. So that means at the end you get a really low current density. There is a very interesting. We are working together with the universities, and there's a very interesting thing. There is a factor. It's called 0.3 amps per square millimeter. This is the maximum allowed current over the motor bearing. If you're exceeding that, no bearing producer gives you a guarantee on the standard lifetime. But this is a little bit complex thing, but we can talk on the booth about that if you want. Okay, good. What happens if I put more cores in it? Because our sales is starting. No, it's at the end. You see, it's getting smooth. That means more and more of the high frequency is gone. So you see, we just added some cores, and so there is a point needed where we have to go to be on the safe side that the harmonics are gone. Yeah, there was one question. What happens if I put in more turns? Very simple. It's working too. I promised it already. But here you can see it. We just put a second turn around this. This is it's like a tube, but at the end it's just stacked cores. It's the same, like a few of them put in a heat shrink. That's all. And at the end, what you see, they are really working better, but with a risk. High frequency, I said it, with the parastatic capacity, so maximum 3 turns are allowed. And this is already very smooth. May you remember it, it was really something like this one before. Okay, good. The next point is, yeah, it helps. What we can do, I don't want to bore, I don't want to tell you too much details. We can simulate that just to have some points. Everything is very nice, smoothly, sinus wave, theoretical. What we can do on the simulation, we can really measure simulate not only the voltages, also the current. And you see the voltage, the current is following the voltage, and that's really very good to the real life. And there's one important thing, what I said to you before. There is something with saturation, and this is all valid on our website. You can download that, or I can tell it to you. That means a core, if the common mode current is too big, what can happen on very long motor cables or on bad grounding situations, that's another point. Then the core can handle a certain voltage time section, and then it starts the current to peak up again. The good thing is,